right, today we're going to tackle a real powerhouse in data science, principal component analysis, or PCA for short. And hey, don't worry, this is not going to be some dry math lecture. My promise to you is we're going to build a real intuition for how PCA finds the hidden stories in your data, how it simplifies all that complexity without losing the main plot. So let's dive right in. So to get started, just imagine a fast-paced soccer game. It's totally three-dimensional, right? You've got players running everywhere, the ball's flying through the air. It's just controlled chaos. Now, a photographer has one shot to capture the most important moment. Is it the winning goal, the dramatic save? How on earth do they pick that one perfect angle that tells the entire story in a single, flat 2D picture? Well, that's it, exactly. A great photographer doesn't just plant their feet and hope for the best. Nope. They're constantly moving, searching for that one perspective that shows the most action, the one that separates all the players with total clarity. And in the world of data, PCA is that photographer. It's always searching for the best possible angle to look at your dataset. And that's the real key here. We're taking a complex 3D world and we're collapsing it into a simple 2D image. We are literally reducing the dimensions, but we're doing it in a smart way. A way that holds on to the most important information, the actual story of the game. And that, right there, is exactly what PCA does with our data. Okay, so with that photographer analogy locked in our minds, let's get a little more specific. What is PCA, really? And how is it any different from, just deleting a few columns from your spreadsheet? So at its core, PCA is a feature extraction technique. And you really got to pay attention to that word extraction, not selection. It's not just picking your best existing features. Instead, it actually creates brand new, totally artificial features. We call them principal components, and they are basically powerful summaries of your original data. Let's make this super concrete. Feature selection is like looking at data for predicting house prices and deciding, rooms are more important than washrooms. So you just delete the washrooms column. Boof, it's gone. But PCA is smarter. It does feature extraction. It looks at the data and says, whoa, hold on, both of these are important. So it creates a new feature, let's call it flat size, that intelligently combines information from both columns. It extracts the essence instead of just picking sides. Okay, so how in the world does PCA create these new super features? Well, the secret sauce is a little concept called variance. Let's dig into the geometry of how it all works. So here's that problem again, the one that feature selection just can't solve. If you're trying to predict a house's price, the number of rooms and the number of washrooms are probably both pretty darn important, right? If you drop one, you're throwing away valuable information. You're just stuck. And this is where PCA just shines. Instead of being stuck with those original axes, rooms and washrooms, PCA finds a totally new perspective. It mathematically rotates the whole setup to find the one single direction through the data where the points are most spread out. This direction, the one with the maximum spread or variance, becomes its number one most important new feature, principal component 1. Then it finds the next best direction, which has to be perpendicular to the first, and that becomes principal component 2, and so on. But why do we care so much about this spread? Why does variance matter? Well, think back to our photographer. An angle with a lot of spread is one where the players aren't all just clumped together in a big mess. You can actually see them as distinct people. In data, maximizing that variance makes sure that the separation between our data points is preserved as much as possible, even when we squish it down to a lower dimension. Okay, this all sounds pretty cool in 2 dimensions, but the real magic of PCA happens when we're dealing with data that we can't even begin to imagine. So let's look at an absolutely mind-bending example. Get this. This is the famous MNIST dataset. It's full of handwritten digits. Each image is tiny, only 28 by 28 pixels. But if you treat every single one of those pixels as a feature, that means a single image is just one data point in a 784-dimensional space. Just try to wrap your head around that for a second. We can barely comprehend 4 dimensions, let alone 784. So how could you ever plot this data to see, if the 3s are different from the 8s, or if the 9s kind of look like 4s? It seems completely impossible. And this is where it gets so cool. We tell PCA, hey, find me the 3 best angles, the 3 principal components that capture the most information possible. And when we project that impossibly complex 784-dimensional data onto just those 3 new axes, the chaos organizes itself. All of a sudden, these beautiful, distinct clusters just emerge from the noise. You can literally see all the ones grouped together here and all the zeros over there. And what's even more amazing is that digits that we think look similar, like a 3 and an 8, they naturally end up clustering closer together. For the first time, we can literally see the hidden structure of the data. And this isn't just for making pretty visuals. I mean, look at this trade-off. If we train a machine learning model on all 784 features, so we get about 97% accuracy. Pretty good. But by using PCA to crush the data down to just 100 features, that's a nearly 90% reduction in complexity, our accuracy only drops by a tiny, tiny amount. This means our models can be dramatically faster to train and run, with almost no hit to performance. That's a huge win. So let's pull this all together. What are the big things you really need to remember about this incredible technique? So the benefits are obvious, right? We get faster model training. We get this incredible ability to visualize ridiculously complex data. It can even help reduce noise. But there is one crucial trade-off. That new flat size feature we talked about, or PC1, it's a mathematical cocktail. It's no longer a simple real-world thing like number of rooms. So we gain a ton of performance, but we do lose a little bit of that direct, easy-to-explain interpretability. I think this is just the perfect way to think about it. PCA is a master summarizer. It reads the entire long book of your data. I'm talking every sentence, every single word. And then it writes the executive summary. It gets rid of all the clutter, but it keeps the plot, the main characters, and the core themes totally intact. Ultimately, PCA is a tool for finding perspective. It's a great reminder that to understand something really complex, you don't always need more details. Sometimes, all you need is to find the right angle to see the big picture. So the real question is, what hidden stories are waiting in your complex data, just one new perspective away from being